Welcome to Energy at Large, the podcast where we talk about the power behind industrial infrastructure. Today we're joined by Blake Bailey with DesignMotors. Blake, thanks for joining us.
Hey, glad to be here.
You want to go ahead and just maybe start by introducing yourself and your company?
Yeah, sure. So, like I said, Blake Bailey with DesignMotors. And DesignMotors exists to provide engineering services and consultation to industrial motor manufacturers, service centers, and end users. So basically what my place in the market is when people have motor engineering needs that are somehow special, something unique. Maybe they've got a large machine that manufacturers can't replace. It was a legacy machine they no longer produce. I step in and I'm able to help people get the same design they had before, but built by some modern manufacturer. I'll help repair shops when they'll have redesign needs. So let's say they've got a machine that's operating in a dirty environment and they've got enclosure issues, but they don't know what to do. The service center feels like they don't want to change airflow. I can step in, and because I've got the design engineering experience at motor manufacturers, step in and help them redesign the enclosure. Maybe they've got to do some kind of electrical redesign on it. I step in and I just provide those new motor design skills to the existing motor market.
And just to clarify, what we're talking about today is industrial motors. We're talking about three-phase motors used in heavy industry.
Yep.
Not anything, like the motor that goes in an iPhone or a smartwatch. We're talking about big motors today. Things like wound rotor motors, permanent magnets for fan walls, things of that nature.
Yeah. So like I said, so I'll work in the industrial world, right? So usually they're three-phase machines. Sometimes I'll play in the DC market as well. So my background is I grew up, my father either running a motor repair shop or a motor manufacturing operation. So I can remember literally being a child in a motor shop, seeing these machines. And then as I got into my teenage years, I was working in the shop, doing disassembly, rewinding machines, putting them back together. Got in the professional world and did some project management for the new motor side. Then eventually went and got my engineering degree and learned how to do the electromagnetic design. And now I feel like I've got a good grasp on a lot of different machine sizes and types, from the inside, out, and then from the outside in, doing the design work. So, I love this industry. Can't really explain to a lot of my friends and just people I meet on the street what I do well. It's not very interesting to them, but when I'm in a crowd like this, I feel at home.
It is funny. We were joking about this on the way over this morning, that a lot of times in our world, a motor is specific. That has a specific meaning to those of us who are in the motor industry. Mm-hmm. It means an electric motor.
That's right.
And oftentimes you'll hear, somebody who works in cars refer to the engine in their car as the motor of the car.
Right.
It's not probably a misuse of the word, but it is to us.
Oh, absolutely. Yeah. My wife's gotten pretty good about it. Over the years, she'll talk. I've heard her correct other people.
Have you?
Yeah, they'll talk about the motor car. Oh, really? That's an engine. I'm like, hey, right,
she's got it down.
Listening.
Yeah, a mistake I only made once working here. I got corrected really quick. So.
I work for an electric engine repair. No.
Well, I mean, we talk about generators, we talk about motors, and so there was some crossover in the beginning where the generator's motor and this other motor. Well, nope, they're completely different.
Yeah.
So awesome. Well, a lot of our audience is going to be end users, maintenance, maybe even some repair shops, contractors. They may know what a motor is,
sure,
but maybe not the history of why motors are the way they are and how they got there. So maybe could you take it back to the beginning for us? Like, how did motors start and how have they gotten to where they are?
Yeah, sure. So, you look at the Industrial Revolution and we had needs for all these new kinds of machines, right? So, you go way back. You look at old mills, they were built right on the stream, right? They had a water wheel that was literally turning a shaft and there was belts hanging out of the ceiling.
Right,
running all these different machines. And they were doing machine work back then, right? They were doing industrial processes, but with natural power. Well, we developed, electricity generation capabilities, and there's, literally the current wars, right? You got Edison and, Westinghouse going back and forth. We're trying to decide, is the world going to distribute in DC, in direct current, or in alternating current in AC? And in the early years, a lot of the technology that they came up with that worked industrially was direct current. So early 1900s, it was DC motors that were doing basically all the jobs out there. And what's interesting, coming from a design engineer's perspective, we learned from mentors with former professors, electrical engineering, a DC motor is electromagnetically speaking only kind of a theoretically perfect machine. So, what do we want out of an electric motor, right? We want to turn electrical energy into mechanical energy, right? A motor has a shaft or something that couples up to the load. It's going to spin something. It's going to spin your pump and pellet. It's going to spin your fan. It's going to turn a conveyor, right? There's some mechanical work that needs to be done. And so, again, what do we want out of an electric motor? We want to do that mechanical job, and we'll be able to control it well, usually. And so, going back to the early 1900s, these DC machines, they were, again, theoretically perfect because you've got great and kind of easy speed control. A lot of times you can control the voltage supply to your DC machine and alter the speed it's operating at. And you can get full torque, your rated torque that you normally get at an operating speed at zero speed with a DC machine, which is kind of the holy grail. Even, you look at nowadays, we've got squirrel cage induction motors that are being operated on variable frequency drives, BFDs. And that's what they're going for. They want control the torque down to zero speed. And sometimes you can be more or less accurate with that. You want position control, or do you just care, how much torque or how much power is coming out at a certain speed? But yeah, so we started with these DC machines, and they were theoretically perfect, except that they've got their maintenance nightmare. From the beginning,
Brushes.
They got there's a bunch of brushes on the back end that are getting that current to the armature, the rotating portion. They ride on a commutator that has hundreds of bars, individual bars that are individually insulated from each other, and you have to upkeep that commutator, upkeep the brushes. Maintenance people have to check on them. You have to adjust even the way the brushes are mounted, or otherwise you get outrageous sparking and you can have issues. So along came AC, ended up, the current wars played out, ended up generating and distributing an alternating current, right? So here come AC motors, right? From the beginning, we had squirrel cage technology, we had synchronous machines, and we had wound rotor induction machines. Squirrel cage machines, they're pretty simple, right? Unlike a wound rotor motor, which has, power that has to be transferred from the rotor circuit to something stationary. And same thing with a synchronous machine. You have to have some excitation on the rotor. You have to provide power on that rotor. Induction motors, they just have that power electromagnetically induced across the air gap. So in that way, they're simple, right? I won't get too engineering here unless you want me to, but anyways, the AC power comes along, squirrel cage motors come along, and it's just like, hey, these are kind of big, dumb machines in a lot of ways, right? Like, they don't have brushes on them. This is great. We don't have to change anything. You apply power to the stator, and the rotor starts spinning. There's some trade-offs, you figure out there, right? You don't have the good control like we talked about with DC machines. You're going to alternate currents, and they have to start thinking about things like power factor, right? And induction machines, by definition, have a lagging power factor, are going to affect the power factor that your whole plant sees. But I think that ease of operation just ended up winning out. And so we saw, probably sometime between the 1940s to the 1960s, squirrel cage machines really start taking over a lot of places. Time goes on, we figure out power electronics, we start to figure out speed control with, early drives or early BFDs, and we start figuring out how to do those things that the DC machine has been able to do all along with the squirrel cage machine. So now it's like, hey, this is great. We've got control of the speed torque characteristics without this maintenance nightmare here. Just at this point, they have to pay for a very expensive drive, right? We're talking about the 1970s and 80s when they're really starting.
And big too. Back then they were massive, physically in size. They were huge.
Oh yeah. Well, I mean, they had to cool the power electronics.
Yeah.
And I mean, I can't even imagine. You don't see a lot of old drives out there. I don't anyway.
They didn't last as long.
Well, that's it.
Back in those times, they've come a long ways to where they're fairly reliable now, across different manufacturers. But back in those days, the drives, they had problems. They didn't last as long.
Mm-hmm. Yeah, that's what I'm saying. It's just funny. I'm having that thought right now. Like
Yeah.
I see lots and lots of really old motors
Sure.
installed. But I don't know, walk across a ton
Yeah.
of really old drives. They're still
Yeah.
out there. Some of the larger ones you will, the LCIs, the load
Sure.
container variant.
Yeah.
You'll see those on the really large machines sometimes. That's about it.
Yeah.
So yeah, talking about the evolution of motor topologies, the DC, the AC squirrel cage machines, and all along you're using wound filled synchronous machines for power generation, right? You go into back there, a coal power plant or even nuke plants as they were built in the 60s and 70s. They were all large synchronous generators, right? So they had to output alternating current, so needed to be AC machines. So that's been there all along. And then you had, you talk about other AC types, talk about the squirrel cage induction, but the wound rotor induction was an early version of speed control that you'd see. And it also helped with starting torque, inrush currents, that we don't so much see today. So, in that kind of in-between time in the middle of the 1900s, there was, again, DC vying for control strategy. You had wound rotor machines that people were using because they were saying, hey, we need a lot of starting torque, low inrush current, in some way to control speed, or you could use a wound rotor for that. And you could, increase the resistance on the rotor circuit and drop the rated speed a little bit. But the trade-off was it was very inefficient. So, again, we had a lot of reasons people were doing the math and going, gosh, the motor by itself is, maybe 93, 95% efficient on some of these medium-sized machines. But look at all this energy we're wasting with, something like a wound rotor motor controlling our speed, or having to, have this drive that's putting up all this additional heat. So as time has gone on, I've heard and I've seen industry talk about energy efficiency a lot more, just over and over.
Sure, and we see studies all the time, at least once a year, whether it's the Department of Energy or some independent study that shows the total power consumption globally going through electric motors is between 40 and 60% of all electrical use in the world. I mean, that's crazy.
Yep.
So efficiency is a big deal.
Mm-hmm. Huge deal. I mean, and in this age, we hear all talk about data centers. We talked a little bit about that and what's going to happen with AI, global energy demand, and it's a wild thought that you say that you're going, okay, right now it's somewhere around half of the electricity generated used for electric motors. What's the future going to look like, right? And efficiency, I think, is going to continue mattering more and more, because it seems like the world's heading in a direction where everybody's vying for that power, right? There's a lot of people fighting for that. You can't just increase generation overnight. And generation's one thing, then you got to distribute it. You can't do that overnight as well. So, yeah, I don't think the efficiency conversation is going anywhere.
Well, go ahead. Sorry.
Well, I was saying that, and that's where, to me, the efficiency starts tying in as you get through the 70s, 80s, 90s, as people start thinking about energy consumption, right?
That's where you start seeing the EPAC motors change out to premium efficiency, and those standards starting to come in.
Well, you saw people start regulating. I mean, before you would have, I believe, you can go back and you could find old end user specifications for efficiency because they didn't want to consume too much power. They didn't want to pay for it. Or you'd see, think about old Navy specs that would dictate motor efficiency before, a lot of end users need to work, but it's like, well, it makes sense. These are Navy applications. They've got gen sets on there and they don't have to use or carry too much fuel. So let's get the motors efficient and then we won't, use as much fuel to make our power. But yeah, it wasn't till, EPAC came along and when these kind of things started really coming into law and being mandated by governing bodies. But yeah, once that started happening, efficiency became the big deal, and we had to start redesigning our squirrel cage machines. But also, academia was able to come up with a lot of pretty viable designs for industrial applications for things like permanent magnet motors, switch reluctance motors, some of these topologies that wouldn't have been possible 50 years ago just because you needed a control strategy for it. But now we get the power electronics figured out. For example, you can't start a permanent magnet machine unless it's got a squirrel cage built into it without a variable frequency drive. You have to have a drive to that. So some of this stuff is now available to us just because we've got the power lock electronics figured out. Like you said, drives, they're pretty reliable nowadays. And so we've got all these options available to end users now. Everything from the DC machines, which are increasingly more rare. Squirrel cage machines are still the workhorse of industry. That's what we always say. They're still doing most of the work, but then you start looking at specialty applications. It's like, well, efficiency really matters. Well, gosh, you can get, 1, 2, or 2.5 percentage points better efficiency on some models of permanent magnet machines compared to a squirrel cage machine. So the end users will do the math, will have the capital cost and the energy outlay they're going to have over the years. And a lot of times say, hey, this permanent magnet machine makes sense in this case.
So I see that a lot, specifically in new applications. So if somebody's going to build an expansion, they're more likely to look at the newer technologies that are available. Yeah. What if you're an existing legacy plant operator or owner, and you have lots of existing motors, some that go back way in time before the government regulated and required efficiency standards? Sure. What should you do? Should that be part of your game plan, your corporate strategy to lower probably your number one expense, which is electrical costs? And how do you go about it?
Yeah, that's a great question. And we could probably just sit in that question for the rest of this podcast, because so many people have different answers there. More often than not, my experience, what I see in industry, is that people really, when it comes down to it, they'll start off talking about efficiency and energy consumption. But when it's an old established, some installation, some very old plant, the difficulty and the expense related to change out mechanical foundation things, changing control strategies, it ends up that people will stick with older technology for a lot longer than you would think they would.
Because the physical fit's just so difficult to change.
Right. Like I'm thinking about, there's a wastewater plant in New York City that I had the chance to work on a new motor replacement project with. And you go in this plant, and it was probably built in the 50s, 60s, something like that. When they had these old, wound rotor induction motors. So big vertical machines, they've got slip rings on them, so they got brushes riding on these slip rings. And they had they were variable frequency drive. They had these resistor grids installed to control, the rotor circuit resistance, so they could do an early form of speed control.
That's actually, is when we were talking earlier about drives that are out in the market today, resistive drives I still see in the market today. It's not very common, but they're out there.
Yeah.
Keep going. Sorry, there's a big drawback to those.
Yeah. And so talking about this project where this is a good example of a situation where you look at it, and at the outset you go, well, they've got these wound rotors installed, and they've got these resistor grids sitting here that they're using for speed control. That seems like an obvious, almost a no-brainer to say, let's get some, still large vertical motors installed that are induction, but they're squirrel cage, and put a variable frequency dial there, because we can get medium voltage drives nowadays. But in this case, the end user said, no, we're not doing it. There's a whole list of reasons they're not going to do it. Getting the resistor grid cabinets out of there, figuring out how to get the BFD footprint the same place, and finding space for them. We're talking about, a major metropolitan area where plant space is limited. So they're saying, we're not doing it because of that. Our maintenance teams, they know how to change brushes on these machines. They know what to expect. They've got the routes they run. They're looking at rotor voltage and all this. Here's our control room. Here's where we adjust the speed. We don't want to retrain people on this. And you just can't even believe, or maybe you can believe, the resistance that people have to those kinds of things. When, what seems obvious is to go with something modern that they have a lot better control with, right? I mean, they've got, in this case, they had maybe 5 discrete speed steps they could do. There weren't even that big a differences in speed. It's not like they were operating down to 0 speed like you could with the drive. But again, it's these big machines. They were actually, you talk about resistive drives and these resistor grids, they literally just burn the heat, the losses from the rotor off as heat. So they have ductwork at the top of their resistor grids. But they use that heat, they puff it back in just to heat the plant in the winter. Now in the summertime, they don't need the heat, right? It's already sweltering in there, so they just let it go. They just release the heat. And so you're sitting there going, they're consciously choosing something that the inefficiency is literally like coming out of the ceiling of this building.
You think something like that, there would be a return on investment and changing that out would almost be less than 18 months.
Yeah. I mean, I didn't do the math and I'm not sure who did the math, but you would think that whoever did the math, you would say, well, obviously, you have to.
It's a no-brainer. Yeah.
Do you see that same resistance only on like one large project, or do you see it like if you go down to a smaller motor but higher quantity, is that same resistance to just doing the math there?
It seems like it's industry by industry a lot of times. I'll see, it seems like in a lot of when I think about it, sometimes it seems like it's municipalities that struggle with that more. They're the ones that seem more resistant to converting something more modern. You get into some of these industries, some of the process industries or the petrochemical industry, and they know that their downtime is so expensive that they can't afford to be down. So they'll like, oh, I don't have to have brushes or something else that's maintenance intensive. Absolutely, I'm switching over. That math's easy for us. And you'll see that also on the energy consumption, because a lot of these, like you think about like petrochemical plants, some in the pulp and paper end users, they'll generate their own electricity. So they're sitting there going, hey, we're not just paying a power bill to a utility, we're watching what we're consuming to generate electricity ourselves. And so they'll have a little more incentive to upgrade and do something more modern. But yeah, I can also think of other projects I've been involved with where they're like, think of a tunnel ventilation project, get another major metropolitan area where they had motors installed from the 50s again. And they said, hey, we need quotes for all new motors. A lot of them were 2-speed, and they're actually 2-speed 2-winding. So they had to have the right starter configurations for those motors where there's 2 separate windings in the 2-speed machines. And it's an old control strategy, again, old speed control. And you would think, hey, but drives on the ones that are 2-speed 2-winding. Now it's easier, if these motors fail, it's easier to get them rewound. If you need replacements, you can get some kind of general purpose thing off the shelf instead of having to have a custom built 2-speed 2-winding motor. But in that case, they went out to the major manufacturers and they got quotes on that kind of thing. Came back and they started looking at their installations and they were like, oh, well, all these old motors were, the phrase I use is pancakes versus hot dogs.
Sure.
So these old motors are all pancakes, right? They're pretty short going down the axis of the shaft and they're really wide. But the new ones are hot dogs, right? The shaft height is very low, but they're very long. And so they were going, well, crap. We got to rip up all our foundation here. We got to bust up a bunch of concrete, pour new concrete, get new foundation rods, run and all that. And so they started doing the math on that and they're like, well, okay, well, mechanically, this doesn't really pay for itself right now. Okay, let's look at, the control strategies. Again, it came back to our personnel are used to this. Let us show you the SCADA system we got. Let us show you the control system we already have built. And our people know we push this button and that button. This is how we switch from the low to the medium to the high speed. And if we get drives, then it's a whole controls project.
Sure, yeah.
We have to involve, 3 different teams. Whereas if we just replace the motors, it's this one team that we can kind of involve.
So how are you helping people through that? So if you've got a pancake motor,
sure,
and you've got to replace it with a hot dog,
yeah.
What strategies can you deploy to not have to get into replacing the base and the foundation?
Yeah. So for the work I do, I really I try to go for simple. I like to think simple for the industrial users because their maintenance people don't want complicated.
I think we all like that. Yeah, we'd like to hear that.
No, your procurement people don't like complicated either, right? So I always try to. I mean, my world is custom design. Like that's what I cut my teeth in. At designing custom machines and large machines for over a decade. That's what I do, but I always come at it skeptically. Somebody will come to you and say, "Hey, we need this really special thing," and I'm listening to them, and I'm a little skeptical. Okay, let's make sure you need that because you got to really believe in going down the custom special route. Some people do need that. A lot of people do need that, but I try to talk them out of it. So I'll say, okay, let's look at the drawing here. Do we have to do concrete work, or are we able to do some kind of like an adapter base, right? Can we take this, hot dog shaped motor and build a base that's going to get it to drop in where your pancake used to be? And sometimes you can't do that, but according to the motor weight, the motor speed, history of vibration problems, that kind of thing, sometimes you can't do that. So okay, well, we tried really hard, but didn't work out mechanically. And the same things electrically, they'll say, hey, we need this custom machine that's just like the old thing, has control strategy this way. I'll say, okay, well, let me tell you the advantages if you, go down the road of something more modern. And most often it's related to supply chain. Just saying, hey, if you switch over to, hot dog style motor with a drive, when this thing fails and you can't get it repaired, you're going to be able to just buy something off the shelf from multiple.
I see. So in a lot of cases, it makes sense to do the upgrade before it's an emergency, before the other motor fails, and you can't find a replacement, or you can't get it repaired in time.
Exactly.
And so if you can change that out proactively, you're ahead of the game. And now you've got common parts that are available anywhere. Yeah, that makes a lot of sense.
Yeah, and a lot of people don't realize how special the motors they have are. Right?
Well, how would you know? So if you're operating a legacy plant, how would you know that the motors you have are obsolete? They have been for 50 years, and you can't replace them if they've just been running.
Yeah. Well, a lot of them, we were talking about this earlier today. You talk about the difference in old and new machines. One of the differences you can see is the newer machines, due to improvements in the insulation systems, will generally run hotter. So people don't know how special they are because they've worked at a plant 30 years and the same motor's always done the same job and it doesn't fail. There's like, well, yeah, it's just a piece of equipment. It's just there. I'll sip my coffee on it sometimes.
Yeah, you hear the adage all the time. They don't make it like they used to.
Yeah.
And the new motors today, you have your hand close to it. You'll feel the heat coming off, like you mentioned.
Yep.
Compared to some of these motors that were built 50 years ago, they're cooler to the touch. You can put your hand on it. Yeah.
Yeah. And so the point of people don't realize what they have is special. That's a conversation that could be difficult too. So you get some end users where I was talking earlier about how they come to you, they know it's special, and they say, we need something special. And I try to talk them out of it. The flip side is the end users or the customers that come to you with something that is special and they don't realize, and they're going, why are you telling me this thing's going to take, 40 weeks to build instead of just me ordering one and it getting delivered 2 weeks from now? It's like, because your speed is so low, nobody stocks this rating, right?
So to catch that, is there something, if I'm a plant manager, can I physically walk through my plant and see something that would tell me I got a problem I need to be aware of? Or is it harder than that?
Do you mean from a procurement perspective, or
what I mean would be, if I'm a plant manager, I'm walking through my facility.
Yeah.
Is there any advice you could give me on what to look for to identify this specific application or this asset, this motor, is going to be a problem for me to replace?
Yeah, I would say vintage is one thing. If you've got a motor that you're dealing with that was built, before the, early 80s or sometime in the 70s, there's a good chance you're going to have trouble getting an exact drop-in replacement for that thing. And the larger the machine, the truer that is. And so I would say, especially when you start talking about large machines, once you get to the, to me nowadays, it's about the kind of couple thousand horsepower range where people start putting different size motors in different frames, right? So there's not a lot of standardization. Our industry, we talk about above NEMA motors here in North America, because NEMA, the National Electronics Manufacturers Association, they regulate lots of things about electric motors and other products too. But one of the things they regulate in NEMA MG1, the motors and generators standard that the whole industry uses here, is dimensions. So if you go up to what's called NEMA 580 frame, you can go into NEMA MG1. It's going to tell you what the shaft height is, what the foundation bolt pattern is, the size of the foundation bolt holes, what diameter the shaft should be, how long it should be, all these things. Well, if you go before MG1 standards, and even leading up to MG1 standards, they had a lot of pre-designs they did for frame sizes. So as you get older, again, 80, 70, something like that, you're going to have issues. You're going to find that the modern frame is usually smaller. So usually it's going to be an adapter base in there. Put something in. But
Do you see a lot of these problems happening in, like, I'm thinking of heavy industries like power generation and water. A lot of that infrastructure in our country was constructed during the 50s and 60s. Do you see a lot of challenges in those applications?
oh yeah, absolutely. And especially in the big machines, because there weren't standards. There's still standards. So people will call and they'll need to replace maybe a big circulating water pump at a plant. The motor that drives the circulating water pump, and they'll say, "Hey, we've got a 1,500 horsepower, 1,200 RPM motor. I need to replace it." In their mind, it's just like, well, you go out, you just get quotes on them. They're kind of all the same. Well, no, it turns out you get this large. They're not. They're all special. All the frame sizes are different. All the limit dimensions of the machine, where the air comes in, where the air goes out, it's all different. So, yeah. I guess I'm still trying to answer the earlier question about what people watch out for and know they got something special. So you watch out for how old it is. The larger it is, the more likely it's special.
Do you have kind of like to kind of pause there, a rule of thumb? Like, I hear about U-frame motors, I hear about T-frame motors. Is there a certain size where you say, hey, this is large enough, I'm not going to have a standard? And that's where, below that, maybe you're a little more safe than above.
Yeah, that's what I was saying. To me, it's kind of around 1,500, 2,000 horsepower or something like that, where above that, I'm like, you're probably going to have to look at this a second time and make sure that you got the right horsepower, speed, voltage, frame size, and closure. Because manufacturer can vary a lot. If you're out there trying to get quotes on, a 30, 50, do like a 200 horsepower motor, there's going to be a lot of people offering the same thing. You talk about like U-frame and T-frame motors. There's a genesis right there that happened in standardization. That was one of the first standardizations on industrial electric motors was U-frame dimensions. When they went to the T-frame, all the dimensions changed a little bit. And so we've had that change. And I've actually heard some talk that we might be looking at some reassignments of frame sizes nowadays because we're pushing efficiency further, and that's changing some characteristic things about some machines. For example, you look like squirrel cage motors. So you need the efficiency to increase on these things. That means you need less losses in the motor, right? Well, one of the ways you can do that is to, for example, lower your stator winding, the stator copper losses or the rotor copper losses, right? You need to decrease the resistance of those circuits. So you need to stuff more copper in the rotors, basically. So sometimes it'll come out where they're going, oh, we had to make the lamination diameter a little bit larger, but we can't make it any bigger because the shaft height's limited on these. So it's like, oh, okay, is this another problem where the industry needs to redesign standard shaft heights? I don't think we're at that point, but I think we're to the point of trying to make concessions in other ways. Another way you can do it is make the motor longer, right? You put more active material. So motors have laminations and then make up the steel cores where the windings go through. You put more of that in there, you can get more copper and you can get more lamination material in there to lower all those electrical and electromagnetic losses to get your efficiency up. But it's hitting a point where, we're going to these, we've gone through IE3, going to IE4, talk about IE5, the super premium levels of efficiency where it is really difficult to get squirrel cage machines as efficient as these levels are. And these efficiency levels are decided on by industry groups, right? It's a group like NEMA or the Department of Energy kind of leading the way and saying, hey, we want to talk about this. And they'll get motor manufacturers involved. They'll get end users involved. They'll get utilities involved. And so there's industry inputs on these things, but it just always, it kind of blows my mind sometimes. I'll look at it and go, wow, this is the goal. This is very difficult. And it's kind of an interesting thing talking about like the work I do with efficiency, because what I'll end up seeing is I've seen a lot of the smaller and mid-sized players, they almost get squeezed out of the market a lot of times because they can't, it becomes the law of the land. Like efficiency it's legislated, it's law, right? On certain motors, they're regulated by, these federal regulations that prevent you from installing a motor that has efficiency below a certain level. And not only that, you have to have it, stamped. You have to get a number from the Department of Energy that they certify that, yes, you built enough representative samples, tested the representative samples, sent us the results, and we agree that your motors are this efficient. They meet this efficiency level. So it ends up becoming a huge capital thing for motor manufacturers where they're on these industry committees consulting on the efficiency levels. And so they know what's coming. So they can go and start doing the R&D efforts and investing in, the new tooling they got to do and figure out what their designs are. Where small players and the medium-sized motor players, they can't even do it. They're like, well, you can't spend, X millions of dollars to invest in all new tooling for a motor.
That's interesting. I hadn't thought about that in terms of limiting competition.
It does in a lot of ways. And, it becomes one of these, there's a lot of industries like this, right? Where competition gets limited in some specific way. But in our world, I absolutely see it. And I've even gone back, I've read comments over the years on the efficiency legislation where they'll, because it's all public record. So you can go back and read. And I've seen comments from some of the specialty manufacturers. They're going, hey, they're kind of raising their hand and say, we're going to get squeezed out of the market here.
Crazy.
What about competition? And usually that doesn't lead anywhere, unfortunately. But
well, let's talk about that for a minute. So not about the competition side, but from an end user perspective.
Sure.
So we see the market's evolving. Energy consumption and energy demand is increasing. Electrification is increasing. We're seeing, a big boom in data centers, power consumption from AI and other things. If you're an end user who has equipment, what should you be doing today to be prepared for the changes that could be happening 5 or 10 years out as energy becomes more expensive and regulation steps in to the next level, perhaps? What advice would you have for somebody in that situation?
Yeah, there's a couple of things I think about. People talking that way. First thing, I was talking earlier about how really try to push people to try and get something standard if they can. Maybe you have to be creative about how you install it, but try to get something standard because we're into a world where everything is becoming electrified, right? Where EVs are more popular than ever. We're trying to electrify aviation. Anything out there that we could put a battery on and run the process with a motor, we're trying to do, which to me makes sense actually, that you're electrifying everything because if you can figure out how to store the energy, we can figure out how to generate the electricity sustainably. Why wouldn't you? Why do you need to burn fossil fuels and have combustion engines doing work that could be done in a way where the generation was kind of a net zero to anything in the outside world? It makes sense in that way. But the flip side is that, you've got to think about what does that mean for the supply chain? So we talk about what we'll do, get the standard product. Because as the supply chains get squeezed, you want to have options in your suppliers, right? Another kind of specialty thing that I see is, a lot of permanent magnet technologies are available nowadays. And we'll see this in ventilation a lot. It seems like that's where I'll see the most. We call it permanent magnet.
Fan walls and applications like that.
Fan walls. They'll go permanent magnet because, again, they want to have these on variable frequency drives anyway. And like I said earlier, you have to have drive to run a permanent magnet machine unless it's got a specialty cage built into it. So with that, though, comes the trade-off of permanent magnet machines. Those magnets in there, you can't just get them anywhere, right? They're geographically limited where they can mine on this earth and where they're processed. Most of it comes from one country on this planet, and it's not North America, right? So being here in North America, you're looking at your supply chain going, well, if I'm building my plant to have fan walls or using PM machines, I need to think down the road. And what happens if I've got all these fans that are very compact because they've got these, what are very efficient motors that are permanent magnet running these fan walls that are very compact. It's great right now, but 20 years from now, we have a big issue with these countries that supply the materials for this. What are you going to do? You've got a fan wall that you better hope to figure out squirrel cage technology in between now and then to replace those things in the same.
Yeah, that's a scary thought, actually, to have a situation where you cannot replace, and any replacement option that is available to you is physically not going to fit.
Yeah. And so that's That's what I think about. And most businesses don't and probably shouldn't operate in, fear of things like that. But to me, it's a real consideration. And I don't know, I mean, even procuring motors, if y'all see now where you're like, oh, the lead time was this, and then, we had this certain thing happen, a port shuts down somewhere, or tariffs hit, or some trade deal happens, and all of a sudden, it's not a 2-week lead time. It's 30 weeks.
For us, since the pandemic, things have been wild. And it's just one event after another, whether it was supply shortages as a result of the pandemic, or if it's today, it's tariffs. We expect to see some changes based off of the raw materials that are consumed in EVs and in data centers and in electric motors. It's the same raw materials. We expect to see at some point that supply chain to get squeezed a little bit harder than it is today.
Yeah. But it's something that, you got to feel for the end users, because we'll get some bad news. I'll make a call to a customer and say, hey, here's what's going on. And they're like, yeah, I've got this call 4 times already today from every part of this project.
Yep.
And so it's one of those things where you start to look at it as a whole system.
Yeah.
And so it's definitely tough, where this is just one component of any upgrade, of any construction.
Yeah.
But yeah, it's definitely unique. I think a lot of people don't know how much goes into a motor and how many different components from so many places.
Yeah. Yeah. No, it is a very global supply chain.
Do you feel like we're entering a point where we're sacrificing reliability for energy efficiency?
I've absolutely seen that in cases. Yeah. And people, you talk about what do end users need to know. That's a great point right there. I mean, keep your head on straight when you're, sourcing these machines, and you might have some corporate directive about energy efficiency. That's again, good policy. Why would we consume more energy than we need to on this planet? There's not a justification for that, right? I just want to burn energy because I want to burn it. That makes no sense, obviously. But, when you just take these, corporate specs, a lot of times they come down and say, we need everything be more efficient because we said in our shareholders meeting that we're going to, be net zero by whatever date. It's like, okay, now we take that out to the field, and we've got, we'll talk about like a squirrel cage design. One issue that we've seen over the years with efficiency improvements in squirrel cage machines is, I talked about how you need less resistance. You need more copper in these machines. Well, what ends up happening is these designs end up producing a higher locked rotor current. So your inrush current. So there's a couple of things that also happen, but I'll talk about the inrush first. So you redesign these machines, you hit these efficiency goals. Great. We're hitting the Department of Energy minimum levels, and people are saving energy when they're up and running. But the first time they go to start some of these energy efficient motors, they hit the start button, it trips offline right away. And it's because, well, they replaced an old motor that was less efficient, but it had lower locked rotor current because the resistance characteristics inside the motor were completely different. So they're going, well, crap. I didn't see that coming. Now I have to change out our breakers, allow for higher locked rotor current. Or in the worst case, I've seen people at, the end of a line or very remote plant where they've got very weak voltage supply. They put these energy efficient motors in, it drags the whole plant down, right? It just brings the voltage to a level where they're tripping other things offline. So you've got some side effects like that happening. And these are real things in industry. So much so, again, you talk about industry specs. I believe they're looking at new NEMA design classes because we have letters that designate general performance of electric motors in industry. They're looking at new definitions for those just based on these things, like to allow for higher locked rotor currents than they did in the past. So it's kind of interesting that you're taking a step forward in the efficiency world, but performance goes, oh, you actually got to take a step back.
So to clarify, those letters, is that like the torque curves, the torque characteristics?
Correct.
What you're talking about?
So they'll, like you talked about, like the most common design letters, a NEMA Design B in North America. And all the letters regulate the same thing. They just regulate locked rotor torque, the minimum breakdown torque, pull-up torque, inrush currents, and they'll usually regulate what speed the motors operate at from their synchronous speeds out. Like they can slip away from synchronous speed or full load. But yeah, so they're considering changes to that. Some other unintended consequences when you talk about energy efficiency and are we sacrificing reliability? We've also seen that
these energy efficient motors, because they've got less losses, that there's usually squirrel cage induction. Again, I don't need to get too engine nerdy, too deep into this, but one other thing that happens is because the motor losses are lower, it actually brings the rated speed up of these machines. So if you take 4-pole machine, if maybe it was operating at 1710 RPM for an older design, it's less efficient. You get that more efficient design, it might be up to 1750. Well, who cares? It's 40 RPM. Well, then you go look at your pump characteristic curve. You're like, well, shoot, it's centrifugal pump or centrifugal fan. And the faster I run it, the load actually increases. So then you have to end up doing, it's not just a straightforward, my motor pulls this many amps for this horsepower, and then I got a new, more efficient motor that pulls this many amps, and my efficiency numbers is much better. I'm gonna save this much energy. Is like, well, actually now you're running at a higher horsepower.
So you're telling me that you're saying that you could introduce a higher efficient motor and have a net outcome of consuming more power based on how it affects the affinity laws on the pumps?
It is possible. It usually doesn't come out that you're using more.
Sure.
But usually it comes out that your savings are actually different than what you expect.
I see. Yeah. So you might not be saving as much or anything potentially.
Yeah, because your actual, the load point you operate at changed.
Fascinating. Yeah.
Because pump designers and fan designers are used to normal slip speeds for induction machines, and they'll design the fan curves and say, okay, well, we know their 4-pole is going to operate on 17, whatever. 2-pole is going to be 35 kp, who knows whatever. So they designed it with one thing in mind, and also other things can run just a little bit faster because it's more efficient. So, yeah, I think those things aren't directly reliability, but they are operations and things that unintended consequences. And when you start looking at how does it really affect reliability, I would say the thing I think about more is we talked about temperature earlier. Motors, the trend is to allow higher and higher temperature rise in the motors because insulation systems are getting better. When you're back in the 40s, 50s, like these old projects I was talking about, they had Class B insulation systems in them. So you couldn't have them a temperature rise that exceeded about 40 or 50 degrees Celsius. You get into the 70s, and for a long time, the Class F insulation system's been the standard. So, it's a 50, 60 rise. You're going, okay, well, now we're going to start allowing rises that are 85, sometimes 100 degrees C. And because we're doing that, we can actually make the machines smaller. Now we've got Class H insulation systems, Class N insulation systems above that. So people are kind of slowly pushing the operating temperatures of the motors up to get them more compact. And to me, that has there's a pretty high correlation between operating temperature and reliability, because you're not just thinking about the temperature of the windings, right? You've got the bearings that are in there that the shaft is riding on, and they're sharing some of the ambient air that's getting to see more heat because you've got this more compact motor running more hot. You've got the whole cooling system needs to be designed around the temperature rise, right? So you've got to reject more heat. Well, that means you got to change up your fan and however that's designed. So to me, that's where my mind goes, is the operating temperatures being allowed to increase, and that's affecting reliability. But otherwise, to me, most of the unintended consequences are more application issues, and you end up not getting the full deal you thought you would because you have to change more equipment than you thought you would have to, and oftentimes savings should start there because you might change your load point.
Well, that might be a helpful, like a good transition point into, from your experience, what mistakes have you seen people make as a motor designer? What mistakes have you been able to correct or be involved in? And is there a way to prevent those?
Could I just kind of connecting those 2 points? You mentioned heat, and my first thought was, when you said, hey, there's a lot more heat, my first thought was, well, I mean, go to an open drip, do something that just gets more air. But do you run into issues as an unintended consequence where you say, well, I'm going to try to deal with this heat, but now my motor's not protected?
Yes, absolutely. Yeah, I see that all the time, where that would be a natural thing. They'll say, well, okay, we need to get it more compact. And so, oh, well, we can get it open, because like y'all probably deal with day to day, most motors sold in the industry are totally enclosed, fan cooled, TEFC. So they're completely enclosed machines. They're usually cast iron, will have fins going down the frame. The internals of the motor are basically protected. There's different levels, but you can be around, rain, you can have them in dusty environments, and the internals are protected. Well, the cost there is that, it doesn't transfer heat as well. So generally the machine's going to be a little larger. Go to something like an open drip machine. Now you can exchange free air with the outside world. The motor's going to run cooler. It can usually be smaller. But what's in that free air? What's in the ambient air out there? You got to pay attention to enclosures. So yes, absolutely. I've seen that where people will try to go for something more open because it runs cooler. You also have the advantage of, with an open machine, you don't have that extra fan that has to be built into the motor to run the cooling air across the machine. It's got, some internal blades on the rotor, but otherwise there's no external fan. So you get a little less windage losses happening in the machine. So they're a little more efficient, actually.
And cost, we see all the time that the less components on the motor, the less metal there is there.
Yeah.
Typically costs less. So it seems, if you're not considering the environment, like, why wouldn't I go with an open drip every time?
Yeah. And you've got to look around you, right? I've seen applications where and to be fair, I've seen it go both ways with enclosures. I've seen people overspecify and underspecify enclosures. And that's another one of those kind of devil's advocate conversations I'll try to have with people. So I'll press them on the enclosure choice. Okay, well, why do you need this? You're specifying a TEFC motor, and this is a completely indoors environment. There's not even that many people around it, so you're not that concerned about noise. You can have a smaller machine with less components. If you want an open drip, why don't you want to do it? Our corporate spec says TEFC on all these. So it's like, okay, well, let's be sure about that. Let's look at your application. So yeah, I think that's a really good point to bring up is the enclosure portion. And that's another trend I've seen. There's certain industries that just kind of latch on to things and they go with them for one reason that doesn't always make a lot of other sense. Like I talked about, I'll use the petrochemical industry as an example. You look at you go to an oil refinery, you look at a lot of the old machines, you look at the larger machines, there'll be a lot of the weather protected type 2 machines. They call them WP2 machines in the motor industry. You'll see them installed, and they'll have a few special features to be, basically what we call a class 1 division 2 product, where they can be installed the atmosphere that might sometimes have explosive gases, but usually it doesn't under normal operating conditions. So they have this WP2 machine, which exchanges free air with the outside world. You get new quotes for motors nowadays from a petrochemical customer, and they basically want everything totally enclosed. They usually go with what's called the TAC, the totally enclosed air-to-air cool. So it's got a hood on the top of the motor with a bunch of tubes running through it, but now you have to add an extra external fan, kind of like these TEFC machines, to drive the cooling air through these tubes. So you have this big longer motor with this tall hood on it, where before they had the more simple WP2 style. And I'll see those and I'll say, okay, what changed, everybody? Did the environment change? Did you put a new process machine in there that's leaking a lot of explosive gas and you're worried about this? And usually the answer is no. It's just, well, these are more protected, theoretically. So it's usually a corporate thing. You're gonna just say, hey, we're gonna standardize on these TAC machines for this certain size because it's just less risk of an explosion. And so you're going, okay, well, what's the risk? What is the real risk here? Because you're about to install a machine that's larger, runs hotter, is more expensive when you've had this other thing in here for 30 or 40 years. And it did the job very well and nothing ever blew up. So
you mentioned that there are other fans on things. Do sometimes those requirements conflict where they say more efficient, but more protected, and all of a sudden you can achieve both?
Yes, thank you. And that's actually, I was meaning to go there because that is what will happen. And you'll look at the old machine, you'll be like, well, your efficiency was actually better because you didn't have these extra systems in there. You didn't have this large machine. And it's just kind of customer by customer, whether you can talk them into, hey, I really encourage you to consider a more simple construction for your reliability, sourcing reasons. And sometimes they say, yep, that makes sense. And other times they say, nope, we want it all. And you're like, okay, well, here's an R&D project, and you're going to have something very special. And that gets back to what you're asking about earlier, like, what do you encourage people to do? It's, in those cases, be careful. because you're about to have a custom motor design, which I love. Gives me job security.
Sure.
Right. I love designing custom machines, but I'm also thinking about the end user's procurement process and, supporting this stuff after I'm dead and gone. It's how are you going to get replacement machines for this? You don't want to just have everything custom. You need to find something that's going to get the job done, but it's not completely overspecified.
Okay. Luke had asked about, what other mistakes do people make, especially in the custom world when they're saying, hey, we need to design this, we need to consider things. Any other mistakes you see people coming to you with?
Yeah. So a lot of it comes around, it's honestly the way they're specified. And we talked in the truck earlier actually about, people coming to you with, hey, I need this motor replaced. And one of the questions I'll usually go back to people with is, okay, well, can you give me some operating records? Can you tell me how many amps you've been pulling on this motor? Can you tell me how hot the stator winding's been running? Can you tell me how long it takes to accelerate its load? So we get this operational data and we look at that, and man, there's a lot of value in that. And I see that's a huge mistake I see people make, because they just take a picture of the motor nameplate, email it to their motor repair shop or motor vendor and say, I want a replacement for this. And they just get that thing quoted. When if you go back and you look at their operating average, well, it turns out they're always operating at 70% load. And you go back to well, let me show you the performance curves on your motor that's rated for 100 horsepower, but you're running at 75 continuously. You go down and you go, oh crap, well, the power factor's terrible at that load point. Oh, my efficiency's also lower. Well, should I consider getting a 75 horsepower motor? Yes, you should. You should look at these things, like how you actually operate these processes matters. And there's something to be said for, having margin in a machine, right? Like, don't run everything up to, the red line, up to its limit. But there's also a lot to be said for the physics of how these machines work. And they do have points where their efficiency is the best. They do have points where their power factor is the best. And so you've got to consider that. And people just don't. They just take a picture of the nameplate, send it off, get something new. Or they look at their operating records and they go, we've had vibration problems for years with this motor. Okay, well, let's just quick hit pause. Let's look at it. Can y'all go gather some repair reports from your repair vendors? Can we talk to the maintenance people? Can we ask them what they think is going on? So I think, that's one of the biggest mistakes people make, is just not gathering that information up front. And I can be a little obnoxious with my clients sometimes. I think I'm really pushing for that. But I want a good installation. I want a good, system that's going to solve the problems they've had for years. Because I've been there on the new motor projects when you put the new motor in, and the maintenance people are there day one going, oh, it's still got the dud on there. This isn't your, it's like, what are you? I talk to the maintenance people. They usually don't.
So do you ever see, kind of going the opposite way, anyone coming to you, all this information, a whole bunch of things, and it's, hey, you've got about 1,000 motors on site. This is 2 horsepower. These are a dime a dozen. Do you ever see that opposite problem? And how does someone strike a balance between knowing, hey, here's the ones that are worth diving into, versus this is the one that my local motor shop has 10 of these sitting on their floor right now?
Yeah. So I think that's where the role of, somebody you trust comes in. And sometimes they're at the plant level, but a lot of times they're not. A lot of times it is that relationship. It's usually a motor repair shop that's in there repairing the machines. That's your first check. So in that case, I recommend your most trusted motor partner, talk to them, and they'll help you figure out what's special and what's not. Because in that case, you run a ton of replacement machines. It can be standard. That's what you want. And they've got a bunch of data packs on them, but maybe you can look in the nameplate and go, oh, this thing says it's a NEMA Design B and a standard frame. I see nothing about hazardous locations on the nameplates. Well, this is a standard machine. Let's just get this thing quoted. So I think it's, when you get to the smaller machines, it does become more about quantity. And you get to the large machines, it's kind of, well, it's a large machine. You should really dive in regardless. I don't know if that answers.
No, yeah, that's perfect. I mean, it sounds like there's never a clean rule, and that's part of the issue. And so finding a partner that just deals with this every day seems like a great way to move that forward.
I want to go back to wound rotor motors. We see a lot of those in the field. We see them in mining a lot. what recommendation do you have for somebody with a wound rotor motor today? They're probably considering options to change it out. They're probably wondering if they'd be better just to leave it as it is for a while. What would you recommend?
So what I would recommend is, in general, you try to go to a newer technology. Again, I'd say that because I design industrial well or rotor motors. I've designed several for clients. I've literally redesigned synchronous machines to be wound rotor induction. So, I can make a living off these machines, but I encourage people to go, if they can, look at getting a squirrel cage machine in there on a drive, because that's going to be the best future proofing you can have. Because like wound rotor motors, there's not manufacturers, except in the wind industry. Wind industry is the one place where you see wound rotors. They call them DFIGs, doubly fed induction generators. That's most of what is up tower in wind turbines. That's the one place you see wound rotors now, but those are kind of commoditized. So they built, a Vestas or a wind turbine manufacturer gets 3 models that are in their different megawatt stress turbines. They build thousands of them.
So say I've got a SAG or a ball mill, and I've got a 2,500 horsepower wound rotor motor. When I take that out for the next service, should I consider looking at shorting out those rings and installing a VFD, or should I look at replacing it totally?
Love these questions.
Okay.
That's good. So you're saying, should you look at replacing the motor and the control system, or just change the motor and get a drive?
Right. Yeah.
You were talking about the different combinations.
Yep.
Yeah. So I would encourage people to get there however they can, get to the modern solution however they can. So if you've got the budget or you planned on it, you can just go straight to getting a squirrel cage machine in there on a drive. That should be your end goal. But you can do stepping stones there, right? You could short the rings out. What you're talking about is basically just there's 3 leads coming off the rotor on a wound rotor machine, just short them together, and you've got a squirrel cage machine then. You can do that, but you're still going to lose windings on this rotor. And when you go to get it repaired, you're going to have to have a vendor that can handle that they know how to rewind these wound rotor machines. They know what's special about them. So you're still kind of getting yourself stuck in something that's non-standard, and you're limiting your vendor base there. So, but I recommend getting to the modern solution however you can. If all you can do for a capital expenditure initially is get a drive and short those rings out, start there. There's a real good chance your drive is going to be adaptable enough to where it can operate a squirrel cage machine later on, and you can get to that more simple construction and that end goal of something simple that you can control well. So when wound rotors, even on applications like bills, and you'll see wound rotors on car shredders, because they'll see them on pumps every now and then. You'll see them a lot of times in aggregate plants that are kind of out the middle of nowhere, because again, one thing they do well is they limit the inrush current. So you limit the motor from dragging the system voltage down everywhere by having these resistor grids. You do the same thing with the drive, right? So just spend the money on the drive is how I would say initially. And medium voltage drives are a lot more reliable. I think people are used to, with these big machines, maybe they got quotes 20, 30 years ago on replacing it, and they're going, the drive was way more expensive than the motor, and I don't trust the drive. I encourage you to look at it again now. I encourage you to take a second look and try to get something modern.
Okay. I appreciate that. Now, one other question I have would be on synchronous motors. If you've got a bunch of old synchronous machines, what should you be looking at for the future on those? What are the potential problems that you have, and how do you overcome them?
Yeah. So what you're describing are the wound field type synchronous machines. So synchronous topologies cover a very wide range, right? Like the permanent magnet machines we talked about that could be, you could hold them in your hand, real small something, to, multi-megawatt propulsion motors, not engines.
And
Caught myself there.
Motors, yep.
Yeah.
Motors.
So they can run the gamut in size range. What you're talking about are wound field synchronous machines. So they've got an AC stator like you used to. It's got coils in it, but the rotor has individual poles that have, copper windings on those poles. And so the stator's wound and the rotor's wound. It's not a wound rotor motor, it's a wound field synchronous machine. So those drive a lot of
larger industry processes. You'll see them at paper mills, for example. They'll run things like refiners or vacuum pumps.
And a lot of plants, especially like paper mills, will run synchronous motors because one thing they can do is control power factor. Because we talked earlier about how you're supplying power to that rotor circuit. By adjusting that excitation, you can actually make it to where that synchronous motor is going to drive its shaft load, right? If it's running a refiner,
it's going to turn that refiner. It's going to do its job. But while it's doing that, you can change the excitation on the rotor and start shipping VARs to your system. You can produce a leading power factor. And then you've got all these other squirrel cage induction motors running all these other processes at your paper mill, pulling your power factor down.
Well, you can either just have a crappy power factor and pay your utility bill for that. You could put in power factor correction capacitors, PFCC banks all over the plant and just kind of have some kind of static control. Or you can have big synchronous machines because you've got these high horsepower loads like the vacuum pumps and the chippers and the vacuum pumps and all these things, refiners rather. And you can have the extra advantage of controlling that power factor. So I see synchronous motors as continuing to play a really important role in the market. The only case that I see synchronous becoming a little less important is I've actually been involved on a couple of projects where there were large synchronous machines installed, wound-field synchronous standard, for example, running a reciprocating compressor. Been installed for 20, 30 years, not a lot of issues, except that the customer said, look, I don't love all the excitation components, okay? I've got the main motor, got the main stator, the main rotor that are wound. Then you've got this other machine out the back, the excitation system, right? The exciter. You've got another stator, another rotor there. Then there's a diode wheel on there with a bunch of power electronics that if any of those fail, the whole machine shuts down. You got to get maintenance out there and change them. And they're not incredibly unreliable, but this was a petrochemical industry. And so, reliability is absolutely everything to that industry. And it was such a concern to them that they said, we want to change these synchronous machines out for induction machines. We want to put wound or
squirrel cage machines in. And so we actually did the project to design drop-in replacements for these wound-field synchronous machines. Designed an induction machine. The frame would just go, boop, just bolt down their existing foundation.
Same rated horsepower, same basic rated speed. They had to confirm that they could afford the drop in speed that an induction motor does. So it operates a little slower than synchronous speed. And then they had to also plan, we talk about power factor correction. Their utility supply wasn't designed so they could supply the induction motor with its lagging power factor. So they had to, when they got the new terminal box for the motor, they got a separate terminal box built with the power factor correction capacitors right there. So they just said, you know what, we know the power factor kind of sucks on this induction motor, but we're willing to do it because now we know we're not going to be changing out power electronics on the diode wheel. We don't have an extra little excitation machine out the back. We believe that the squirrel cage is going to be more reliable, keep us up and running. So we're going to put some PFCCs right there, handle that power factor issue, and hopefully have easier maintenance life.
That's interesting. Rather than upgrading the controls on the synchronous machine itself, they opted to change it. And obviously, another route there that we've seen come down in price is active front end, medium voltage, variable frequency drive technology, which used to be inaccessible because of price. Today, it's, if you haven't looked at it in a while, it's worth looking at again. And then you can also ship those VARs back and forth using the VFD itself to compensate.
And what's nice about that is you have active control. As you change load throughout the day and need to operate different points for your process, you can control that. You get PFCCs installed, you can switch some off, switch some on, but it's a static control method, right? It's just you're not able to program things to really optimize your energy consumption. Yeah. Because I think y'all talked about in the last podcast as well, power factor is a big deal and people don't always realize it. They focus on efficiency and they forget about power factor so often. I've seen some specs written in an intelligent way where they talk about the power draw. They talk about, more or less the amperage that the motor's pulling, which kind of covers both. I'm like, hey, that's smart. That's a good way to think about it. But a lot of people don't.
Yeah.
So no, you're exactly on it with another advantage of drives out there.
Okay, we're probably about out of time. I've got one other question for you.
Sure.
If you're looking at designing the facility or the plant of the future, and you're looking at what you have available today, what advice would you give to somebody who's looking to build this new facility to make sure they've got their bases covered?
So I would take in that case, you don't have the operating data, right? So you're going, well, I've got the design specifications for the driven equipment, so that's all I can go off of. I would be looking at the environment. I'd be saying, okay, well, what are my indoor installations here? What are my outdoor installations? Let's have a motor specification written, but it's written with options. It's written with options on the enclosure according to the installation environment. It's written in a way that pushes efficiency and encourages procuring machines that are very efficient, but it takes other things into account, right? So the plant of the future, I would hope that people could design things that are saying, hey, we're going to have things that are efficient and compact,
but they're not going to be impossible to procure. And I don't know how to write it, but I would think about supply chain and just think about where the world is going, because like we keep talking about,
electrical steel, we're going to have to increase our output of electrical steel to make these laminations and these motors to meet the EV demand, to meet the electrified aircraft demand, to meet industrial motor market demand. I mean, transformers, there's multiple things in industry that use the same raw materials. So think about supply chain and say, what's going to be the easiest thing? What do I think the easiest thing to procure is going to be in the future? So think about that. You look at the shiny thing, you look at the permanent magnet motor, and you go, oh, it's very efficient. I'm going to save so much money, or I'm just going to literally use this much less energy to run this thing. But do I have confidence that that supply chain is going to stay the same, throughout the years? So I would encourage them to think about supply chain. And I encourage people to,
I hesitate to say it, but I encourage people to think about using drives.
I hesitate to say it because there are some, if you have just a fixed speed application, and it's fixed speed, and that your machine literally can't operate at a different RPM, okay, sure. Maybe that's a case where you don't think about it. But if you have any kind of advantage that varying the speed would give you, whether in process or energy savings, just go ahead and start thinking about putting a drive on there. So you've got that basic infrastructure built. Your control schemes are built out in such a way that you can adapt to different drives. But I encourage people to use drives, again, whenever they've got some kind of speed control need. And then I encourage people to be open-minded. Don't just say, hey, my corporate spec is written in this way and I'm not going to question it. If you go out there and start getting quotes and you're getting pushback from vendors, then have an open mind and listen to your trusted motor experts. And that's the other thing like we talked about. Have a trusted motor advisor out there. It can be your repair shop. It can be a consultant. It might be somebody that works for you if you're an end user. I've met plenty of very capable motor experts that are inside of these large corporations. But yeah, that'd be some of the things. Simplicity, supply chain. Listen to your experts and have those experts.
It's great advice. Yeah.
Well, it's been great having you on. If someone wants to work with you, where are they going to find you? Website, LinkedIn, what's the best?
Yeah, so they can go to my website, DesignMotors.net. Shoot me an email, Blake@DesignMotors.net. You can look me up on LinkedIn, Blake Bailey as well. But yeah, I'd love to talk to people who got specialty needs or just, I'm truly an independent third party here. I don't produce motors. I'm not a manufacturer. I consult. I do the design work, so I'm usually able to hold a pretty independent and neutral perspective for folks and help interpret. So
great.
Yeah.
Well, you've given us a lot to think about and a lot of good information today. So thank you so much.
Thank you all. It's been cool.
Great.
Thanks, Blake.
We'll see you on the next episode of Energy at Large.